Hi, I'm Bill Anderson, and today I'm going to be talking about quantum computing and post-quantum cryptography. So, about 10 years ago, 2016, there was this news story. It was about Justin Trudeau, who was at that time the Prime Minister of Canada. He was visiting some research institute and was asked by a reporter, I guess it was kind of a joking question, if he could explain what quantum computing was, and he kind of surprised them by giving actually a pretty good answer to that question.
Regular computer bit is either a 1 or a 0, on or off. A quantum state can be much more complex than that because, as we know, things can be both particle and wave at the same times, and the uncertainty around quantum states allows us to encode more information into a much smaller computer. So that's what's exciting about quantum computing, and that's what we're
Yeah, so that's actually a pretty reasonable explanation for a layperson that is not, a quantum physicist or a computing expert. And he's basically right. Quantum computers, they rely upon these properties of quantum mechanics, such as superposition of particles, particle wave duality, and uncertainty, that allows quantum computers to perform computations that are not possible or practical for classical computers to perform. And the two main quantum algorithms we're going to talk about are Shor's algorithm and Grover's algorithm, which are considered to be, the primary quantum algorithms. The main difference between them is that Shor's algorithm is for a pretty specific set of problems involving the factorization of large semi-prime integers or computing discrete logarithms, which, as we recall from earlier in the class, these are the types of problems which ensure the security of a lot of asymmetric ciphers like RSA, Diffie-Hellman, the elliptic curve cryptography. I think we also, we talked about the Al-Gamal cipher that relies on the discrete logarithm problem. So Shor's algorithm becomes very significant in regards to those problems. Now, Grover's algorithm is kind of more general purpose. It allows you to search an unordered database or black box function, in other words, a hash function. So this would be a way to, for example, reverse a hash or to try to brute force a symmetric key. Now, the other difference here is that Shor's algorithm offers an exponential speed up compared to a classical computer, where Grover's algorithm is only a quadratic speed up. So, for example, using Grover's algorithm, if we were going to try to brute force an AES key, we would need we could take a key that is, for example, 256 bits, and we'd only have to search, being the square root of n here, we'd have to search 128 bits worth of space there. So we basically cut the bit security in half by using Grover's algorithm, where with something like Shor's algorithm, you would take a 256-bit key and you would reduce that to its logarithm base 2, which is 8 bits so of search space. So it basically is far more significant in terms of its speed up. However, like I say, Shor's algorithm is applicable to a smaller set of problems, so it can't necessarily crack like an AES key. It can only crack like an RSA or an elliptic curve key. And Shor's algorithm is the one that we're primarily interested in here, because this is the one that has the most potential to actually disrupt our existing crypto systems that are in use today. And we're going to use the example of RSA, since that's the one we studied. And of course, as we know, in the RSA cipher, if you're going to try to determine the private key, you have to factorize the public key, and that requires searching a very large search space, which we say, is the set of positive integers less than or equal to the square root of the public key. And you could say, well, what about it's really just the prime numbers that are less than or equal to the square root of the public key. Well, yes, but you have to find those prime numbers, which when you get to that large of a size is a pretty considerable computation task. And you could also say, well, there's more advanced methods like Pollard's row algorithm, the general number field sieve, et cetera, et cetera. And yes, that's true. I mean, we can definitely do better than just the naive search using a classical computer. However, the key thing here is that it is still, even with those more advanced methods, it is still essentially an exponential relationship between the number of bits in the public key and the time complexity of cracking that key. So in this example, I've used n to be our search space and b to be the number of bits. There's basically a logarithmic relationship there between those two things, and as a result, we can if we express our big O notation in terms of the number of bits, we've got an exponential relationship here. That's if we're using a classical computer. If we're using a quantum computer that has implemented Shor's algorithm, we have now gone from O2 to the b time complexity to OB cubed. So in other words, we've gone from exponential time to polynomial time. And I guess it is difficult to overstate the significance of that shift. And suddenly we're going to be able to crack RSA. And not just RSA, but also elliptic curve and Diffie-Hellman. And also the elliptic curve version of Diffie-Hellman, which we were talking about. Those are the basis of our entire modern system of cryptography that secures the internet, that secures TLS, our public key infrastructure for the entire internet. Now, fortunately, we don't yet have quantum computers that are capable of cracking an RSA key. The quantum computers that do exist are highly experimental. They only have a handful of qubits, a qubit being a quantum bit. They're unreliable and very error prone, so there's still a lot of work that needs to be done to increase the number of bits to improve their error correction and other things like that. But the mere threat of future quantum computers is enough to have people worried about this problem called harvest now, decrypt later. And the concern is that there may be very advanced persistent threats or nation states who are harvesting and storing encrypted communications that are going over the public internet with the intent of, in maybe 10 or 20 years, when there is a working quantum computer, they can go back and decrypt those past communications. And suddenly anything in there that was a really important, sensitive, long-term secret, espionage between nation states, very large corporate or financial secrets, that stuff suddenly is decryptable 10 or 20 years down the line if it's been stored. So there's, a push to move towards post-quantum cryptography today, even though we do not yet have a working quantum computer that can crack this cryptography, for the simple reason that we could, this harvest now, decrypt later problem. And as a result, in 2016, the U.S. National Institutes of Standards and NIST, they put out a call to develop post-quantum cryptographic algorithms. And in 2022, they actually announced that 4 of these had been accepted as, ones that will be replacements for our existing crypto systems in the future. And so there's Crystals, Dilithium, Crystals, Kyber, Sphinx Plus, and Falcon. Of those, the first 3 already have published standards. I believe they're still working on the published standard for Falcon. So these are going to be, the post-quantum ciphers that are eventually going to replace our existing cryptographic systems. There's also an open source library, liboqs, from the Open Quantum Safe project, which aims to develop and integrate applications with quantum safe cryptography. And again, many of these algorithms are still highly experimental. When you read the GitHub of this, they kind of talk about not to rely on these in production yet. And in the meantime, many of these things they're going to be what we call hybrid cryptography, where we're combining a post-quantum cipher with one of our classical ciphers, like RSA or elliptic curve in these different ones that are used nowadays. And the idea being that these newer ciphers are not as thoroughly studied, and we do not, we're not quite as certain about the security. There may be flaws found in some of these ones yet. So we combine these with our traditional ciphers, we can maximize the security. We can try to add a level of post-quantum security while ensuring we have the classical security of the existing algorithm. So we're going to see a lot of this hybrid cryptography kind of during the transitional phase in the next decade or two. In fact, Signal, which is a popular encrypted messaging app, has already implemented its own post-quantum ciphers. In September 23, they added the post-quantum extended Diffie-Hellman, and in October 2025, they added the sparse post-quantum ratchet. So those are some interesting developments, and I think we're going to see more and more examples of this, especially in very security-sensitive things like government and military applications. Already, they're pushing for some of these post-quantum ciphers to be added. Yeah, so thanks for coming to my presentation, and I hope you found it interesting and informative. Have a great day.